Okay, hello, welcome everybody. Welcome to the fifth in our series of Trinity research talks that have been going on this term. We're delighted to bring you another excellent speaker today. If you want to catch up on any of our previous ones, you can find them on our website, and they're all available to watch back, which is excellent. My name's Phil Pass, I'm the Alumni Relations Manager at the college, and it's great to have so many of you joining us today. We had over 250 registrations for today's talk, from over 24 different countries represented. So it's so great to be able to reach out to you and see you all around the world, or not see you as it is, but to feel that you're with us, even though we can't have anyone back into Cambridge at the moment. Hopefully soon, let's see. A couple of bits of housekeeping first. The event will take place as part of a presentation that will run for about 20 to 25 minutes. And then there'll be a Q&A to follow. You can submit your questions using the little Q&A box down on the screen. It'll be somewhere down here or up here, depending on what device you're watching on. So submit those at any time, and we'll come to that at the end of the talk. The event will be recorded, so you can watch it back later on. And don't worry, the only cameras that can be seen will be myself and today's speaker. And same with microphones, so you won't be seen or heard at home, so don't worry about any of that. So today's speaker, we're delighted to be joined by Dr. Hannah Stern, who was elected to the college as a Title A Fellow in 2017. She's based at the Cavendish Laboratory within the quantum optics group. And today's talk, which is called Quantum Light from Atomically Thin Materials, promises to be fantastic and fascinating, and I'm sure will prompt lots and lots of questions. So, Hannah, over to you, and thank you very much for joining us.
Thanks very much, Phil. Thank you for that very kind introduction. And it's a delight and a pleasure to be speaking today to the alumni group. So my talk today is titled Quantum Light from Atomically Thin Materials, or a title that I really prefer is Materials for the Ages. So new materials have always been a bearer of new technologies. And since the beginning of humankind, materials have shaped our civilizations. Our ancestors in the Stone Age used stones, animal skins, and plant fibers. In 2,000 to 3,000 BC, it was found that alloying copper with tin produced a material that was stronger than stone. Thus, the Bronze Age was born. And subsequently, advancement in metalwork led to iron and steel tools that were stronger than bronze, but lightweight. But importantly, each age was named after the material that shaped that age, each material better than its predecessor. But material innovation didn't stop there, and in fact, advancements in material science completely revolutionized the 19th and the 20th centuries. Coal and the steam engine literally and figuratively powered the Industrial Revolution, and advances in lightweight metals, composites, and metal alloys led to globalization. Frank Whittle from Cambridge in 1930 invented the first turbojet engine and was involved in the development of nickel alloys, materials that retain their strength at high temperature. So in the 20th century, a kaleidoscope of new materials have emerged that have revolutionized modern living. Plastics and polymers have transformed home and dress, and they may indeed come to transform energy. In fact, during my PhD here in the Cavendish with Richard Friend, I worked on plastics or polymers that can be used to enhance efficiencies of solar cells. But by far away, the material that has had the most impact upon the 20th century is silicon. Because before silicon, computing power was severely limited. In 1906, Lee de Forest invented the vacuum tube, and this is shown here on the screen, pieces of electrified mesh held between electrodes in a vacuum used to amplify currents. And these were indispensable at the time. They were used in World War I. 1 million were manufactured by the end of the war. And the first computer shown here, ENIAC, was built from 18,000 of these vacuum tubes. And this computer was by no means efficient. It filled a room 100 feet long and consumed 200 kilowatts of electrical power. So it was said when this computer was turned on, the lights in Western Philadelphia dimmed. So clearly at this point, a more effective switch was needed. And this came about from the work of 3 scientists at Bell Labs. In 1947, the first transistor was built. And this was built from a material just beginning to be understood called silicon. And the Nobel Prize was awarded to Bardeen, Brattain, and Shockley, the 3 scientists responsible for this, in 1956. And then this subsequently led to the first full integrated circuit made entirely from silicon, where different parts of silicon were performing different tasks, enabling one integrated circuit entirely from one material. And this was incorporated in the first chip-based computer in 1961, built by Intel. So what is it about this material I'm going on about, silicon, that really has enabled this revolution in the 20th century? Well, what I'm talking about is crystalline silicon, a material made up of silicon atoms, the 14th element of the periodic table. And you may be more familiar with silicon in other forms that it takes, i.e. silica or sand. But the type of silicon I'm talking about is crystalline silicon, which is exactly the material that may be on your roof being used as a solar cell. And crystalline silicon is made up of silicon atoms bonded together via strong covalent bonds into a structure we call a diamond cubic crystal structure. So a crystal made from silicon. And what makes silicon really so useful to us is the fact that it is a semiconductor and it has a bandgap. So by this, I mean energy levels within the material where electrons can reside. So for example, the ground state of silicon is the energy level where electrons are bound in the material and not able to move. And this is where electrons reside when we're not interacting with the material. However, if we put some energy in, energy equivalent to the bandgap, or the energy difference between the excited state and the ground state, then the electrons are able to be promoted to the excited state where they are now free to move through the material, therefore enabling electrical conductivity. So what this means is that we can control silicon to conduct electricity when we want it to, but to not conduct electricity when we don't want it to. And this is what enables it to form a switch, and also enables it to act as a solar cell. So the energy gap here, this band gap, is about equivalent to the energy of light from the sun. So this is what enables silicon to also be a good solar cell. So silicon has really been at the forefront of computing now for the last half century. And as Gordon Moore, the co-founder of Intel, predicted in the 1960s, the amount of transistors on a chip would double every 2 years. So we've really seen this exponential growth in computing power. And this diagram here shows the last 40 years on the x-axis and transistor count on the y-axis. So nowadays, a modern day chip contains over 1 billion components and can fit on the size of a fingernail, just like this. So my question to you today really is, if silicon has been the most important material of the 20th century, then what will be the most important material in the 21st? And I put to you today, as a hypothesis, that we need to think in 2D to answer this question. What do I mean by that? Okay, well, all materials familiar to you are 3D. They have a length, they have a width, and they have some thickness. 2D materials are exactly that, 2-dimensional. They have a length, they have a width, but they have virtually no thickness. So they're the thickness of a single atom. And the most well-known example is graphene. So graphene was first isolated in 2010 by scientists in Manchester. And this isolation, this discovery, was awarded the Nobel Prize. So in the last 10 years, there has been a huge amount of interest in graphene. It's become known as the material of superlatives. It's the lightest material we know. It's the strongest material we know. It's the best thermal conductor. It's the best electrical conductor. And so really there has been a lot of hype in this area. And the electrical conductivity is an interesting one. And to give you a bit of an insight in how 2D materials formed, let's delve into this with a little bit of chemistry. So in this diagram here, I'm depicting a carbon atom with this dot. And the way carbon atoms are bonded to one another in graphene, which is also very similar to the way other 2D materials is formed, is via something called sp2 hybridization. So what does that mean? Well, each carbon has 4 valence electrons available for bonding. Now, 3 of these are occupying these orbitals, or these clouds that I've drawn here in red, called sp2 hybridized orbitals. And turns out that they overlap with orbitals of neighboring carbon atoms, forming strong covalent bonds, and therefore forming this hexagonal structure. As you can see, if you extend this out further and further, you get to the image on the left. Now, I said there were 4 valence electrons. 3 are involved in bonding. The 4th one is what we call delocalized. It's not bound to one atom or another, but it's free to roam about the material. And this is what enables graphene, this high electrical conductivity, that is one of its real selling points, and has led to many people thinking that this must be the foundation of the material that will define the 21st century. And that way may well be true, but I'm actually here to talk to you today about a different 2D material that I think also holds huge promise to be important in our lives. And this is an analog of graphene, and it's called hexagonal boron nitride, which is quite a mouthful. So I call it HBN for short. And what HBN is made up of is the 2 elements that neighbor carbon on the periodic table, it's boron and nitrogen. And these are bonded together via similar bonding in this hexagonal arrangement. Now, what makes HBN quite interesting is that it also has a bandgap. So like silicon, there are energy levels in the material where electrons sit at rest. And then if they are given a certain amount of energy that is equivalent to this bandgap, they can be excited. But unlike silicon, where this energy gap is about the energy of visible light, in HBN, this energy gap is about 3 times greater. So most of the time, HBN is in fact an insulator, and electrons are not moving at all. Now, if HBN is an insulator, then why on earth is it interesting? I've been interested since my PhD in how materials interact with light. So what's the story here? Well, it turns out that if one of these atoms in the structure, boron or nitrogen, happens to be missing, or if we have the inclusion of another atom in their place, we form what we call an atomic defect. And it turns out that these defects in HBN do interact with light because they introduce new energy levels in the bandgap, enabling electrons to be promoted. So that means that if I excite this material with a laser, for example, as shown by this green arrow here, then these atomic scale defects will absorb the light and re-emit it. But the way in which they re-emit the light is not like any other light source that you might be familiar with. It's inherently quantum in nature. And quantum light sources are highly sought after at the moment, which I'll come to explain in a moment. So what do I mean by emitting quantum light? This is probably sounding quite abstract at this point. Well, let me walk you through this. All light sources can be described as either classical or quantum. And I'll go through this example using the idea of the photon. So the photon is an elementary particle. It's a particle of light. Now, if you imagine a light source, which is emitting photons over time, consider a light source where the arrival time of these photons is completely random. So there is a regular spacing, and to an outside observer, this light source looks even in intensity over time. This is what we call a coherent light source, and light from a laser operating below threshold would fit this description. Now imagine a second situation where the light is still random, but much more chaotic. So photons may be emitted in small bunches, and then a large gap, and then small bunches again. This type of light is appropriately called bunched light, and the type of light that follows this behavior is thermal light from the sun or light from a discharge lamp. So what's important in both of these cases, it's very difficult to predict when photons may arrive or may be emitted. And it's quite possible for 2 photons to be emitted at the same time or arrive at the same time at a destination. And it turns out that both of these types of light sources satisfy equations that describe classical light. So we can think about them in the photon picture that I've drawn here, or as waves. However, there is a third type of light source, which you probably have less experience with day to day. And this is one where photons are emitted very well spaced from one another in time with regular spacing. So in this anti-bunched light, there is an ultimate limit as to how close two photons can be emitted to one another. And it turns out that this light source simply cannot be described or fit into the classical models. And so therefore, observation of anti-bunch light is an inherent quantum phenomenon. So why are we interested in this? Actually, an extra point there, light that sources that emit anti-bunch light are single atoms, single molecules, and in our case, single defects. But why are we interested in sources like these that emit quantum light? How can this be useful to us? Well, it turns out that quantum technologies that are emerging at the moment require materials that are quantum emitters, or that can emit single photons over time that are well separated from one another and identical. And the types of quantum technologies I'm talking about are quantum communication, where single photons are used to send information, or quantum encryption, where photons are used to encode and decode information. And quantum encryption is a good example, actually, to explain how photons can be used for these types of technologies. So I have a small diagram here, which I'll show. But first, so what is encryption? Well, classical encryption methods have been used for decades to send secret messages. A very well-known example is the Enigma code used during World War II. And of course, the Enigma code was eventually deciphered by mathematicians at Bletchley Park. And this is a great example, therefore, of how classical encryption methods have an inherent weakness, in that it's impossible to know if someone has interfered with the message. So quantum physics thinks they have an answer to this, and that's quantum encryption. And the way this works is if, let's say, Alice wants to send a message to Bob, and she's going to do this using photons. What she does is she prepares a photon in a particular quantum state, and we'll say she's preparing this photon in a particular polarization, which I've depicted with this arrow. So in order for Bob to decode the message, he must first detect this photon and perform a measurement of its polarization. If he gets the same result as Alice, then they set up a link and they can share information. Now, let's say there is an eavesdropper who wants to interfere with this but remain anonymous, Eve. So in order for Eve to interfere, she has to receive the photon and perform a measurement. And due to the quantum nature of this measurement, the measurement itself will be invasive, and it will change the quantum state, the polarization of the photon, meaning if she then tries to send it on to Bob, he will get a different answer from Alice. And this is the essence of quantum cryptography. And far from being an academic intrigue, it's actually a technology that is being explored and currently exists in the world. And in reality, it's a single photon source, a material, perhaps something like HBN, sending a photon down an optical fiber to a single photon detector. Or it can occur through free space. And this is something being explored at the moment. Just this year, there was a record set of 1,200 kilometers for free space quantum cryptography. And this was by a Chinese group that published in Nature this year. And furthermore, industry in the UK is definitely investing in these types of technologies this year. A big collaboration between British Telecom and 20 other partners, including a spin-out company from our laboratory, are working to enable 5G quantum communication. And of course, if you see this image here, in order to really enable a technology like this, even within cities, we require a material that can reliably, reproducibly produce quantum emitters or single photons over time that can be used for this technology, ideally in a very small device in miniature and at room temperature. So it turns out at the moment that hexagonal boron nitride is one of the leading candidate materials for this, for the very reason that it works at room temperature very well, and is inherently a two-dimensional material, so easily incorporated into current devices and future devices. So one question some of you might be wondering now is, how on earth do you know if you have a single photon or a quantum emitter? These are very short, small length scales we're talking about, and time scales. So it turns out there's a very elegant experiment, which is simple to explain, that we perform quite regularly in the lab to check that a particular defect is acting as a quantum emitter. So how this works is we have a light source, and so I've put this cartoon here of HBN, and we send the photons that it is emitting to something we call a beam splitter. So it's a bit like a mirror, except that it sends 50% of its photons to detector 1, and 50% are transmitted to detector 2. What we then do is we monitor the arrival time of all the photons at each detector. So every time a photon arrives at detector 1, we write down their detector and the exact timestamp of that photon arrival time. We then compare the arrival times between the two detectors, subtract one from another, and we form a histogram of the difference in arrival times. Now, if we have a classical emitter, remember I said before that classical light sources have photons that arrive quite randomly in time, and they may come out in small bunches and at longer time delays. If we're the classical emitter, then there's no guarantee that when the time at which a photon arrives at one detector, we won't also have one arriving at the second detector. In fact, our distribution of time differences will be completely random and look like a flat line, effectively. However, if we have a quantum light source, remember there is a limited time space between each photon being emitted, meaning that it's impossible for a photon to hit detector 1 and detector 2 at exactly the same time. So when we draw this histogram and we look at 0 time difference between the two detectors, there should always be a drop-off in counts or coincidences. And this is how we do this measurement, and this is a typical type of kind of data we get for this. So on top of measuring our single photon emitters, we also have to go about finding them and actually creating them in the first place. So there's a decent amount of material science that we do. And the types of tools we use in the lab are a range of microscopies, actually. So the types of confocal microscopies that one might find in a biological lab to look at specimens, or a chemistry lab. So this is a kind of artist's photograph of one of our setups, where we have a laser bouncing around through different optics and mirrors and then sent down into this objective. So just the type of objective you've had on a microscope. So a lens focusing our beam onto our sample, which you can't really make out here, and then our stage, which moves our sample around in X and Y. So we can scan around and look on the kind of micrometer length scale as to where we're seeing light emission, and then zoom into that region to study it. We also use techniques that are more familiar to biologists who want to look inside and observe the structure of cells beyond the diffraction limit. So we can do this in our 2D materials, and this is a little image of a wide field microscopy video of illumination of our 2D material, and we're observing light emission. So whilst the bulk of this is dark, because HBN is an insulator, not absorbing light, the sites, these defects that do absorb light are blinking. And so they blink on and off between two discrete energy states, and kind of further confirmation that we're dealing with a single light emitter. So an extra thing that we're working on now, and I've just thrown this in as a last slide, even though it is a bit more detailed, is we're interested in trying to understand if these defects have any more kind of quantum properties that could be used in future quantum experiments or technologies. And one of the important ones is spin. So you may have heard of spin before as a kind of the two-handedness of of an electron. And it turns out that these defects themselves, the excitation, can have spin. And the way we go about measuring this is applying a magnetic field. For if a state has spin and we apply a magnetic field, we observe a splitting. So we actually observed some kind of spin multiplicity to the state. And if we apply frequency that matches this energy splitting, we should see some overall change in the photons being emitted, the photon rate. And so this is what we do in an experiment called optically detected magnetic resonance. And recently we observed actually some kind of feature at a particular energy which we believe corresponds to a spin splitting, suggesting that our defects are not only very good quantum emitters, but they also have other quantum properties that might make them interesting for other technologies. So this is really still a work in progress, and this is what we work on at the moment. So pulling back a bit, just to summarize, I've talked today about 2D materials and asked the question, are 2D materials the material of the future for us? And this is something that will, I guess, come to be answered in the next few years. Certainly, there has been a lot of hype around graphene for use as a sensor, batteries, drug delivery even, and certainly materials like HBN could be used and are being explored in quantum technologies that require photons. An important point to make here is that these 2D materials are often used together. So a device would very rarely be made from HBN without having a layer of graphene in there too. So heterostructures, as they're called, mean that the combination of several 2D materials, the sum of this is really greater than the sum of its parts. So there is a lot of promise here, and we'll have to see which of these technologies really comes to the forefront. But whether the future be a 2D material future or a graphene future or whatever, it's clear from history that human ingenuity and advancements in material science have really been instrumental in revolutionizing living. And hopefully this continues into the future. I have faith that it will, and that we can use material science to answer the big questions that we have in healthcare, disease, poverty, and energy. So with that, just like to thank you everyone for being on the call, and I'm very happy to take questions.
Thank you very much, Hannah. That was fascinating. There's lots of questions starting to come in. I don't know if you can see the Q&A box as well. I think we will start with Patrick Cadell. Would quantum cryptography render communications uncrackable and immune to brute force computing attacks?
Yes, so that's a very good question. So the thought at the moment is that, so first of all, I guess I should caveat that I'm definitely no expert on the ins and outs of quantum cryptography and quantum computing, but what is thought is that the current encryption methods that are used, which are generally very complex mathematical problems that take classical computers a long time to solve, will be very easily cracked with quantum computers. And so that's really the motivation to move to a quantum safe cryptography method, it's quantum computing itself. So it's thought that these quantum safe methods will be a lot more robust. They won't be able to be solved by a quantum computer because of the inherent randomness. We're relying on quantum physics itself to provide the encryption. I don't know if there's any other kind of weakness in these methods. There probably are. A lot of it comes down to the reliability of the photon source, for example, which is why the material science aspect of it is so important. If the source is unreliable, or there are high losses in the system, or for example, losses in the optical fiber used in quantum cryptography, then this can make the encryption method less reliable. But if working properly, should be a lot more robust than classical encryption methods.
Okay.
I hope that answers the question.
I think so. There's a couple of questions about defects in here. There's one about from Mike Edwards. It says spin equals half of these defects. I know you've got something to say on that. And John C talks about defects as well above that. Since HBN, it says what other types of defects are being investigated, e.g. adding atoms from different materials. So I don't know if you can just touch on that.
That's a really good question. So one of the great things about this field, which I love, is it's very young. It was only discovered a few years ago that this material interacts with light in this way. And we still don't know the structure of these defects. So I can't tell you today, oh yes, it's definitely one boron that's missing, or it's definitely one nitrogen. And you'd think this could be simple to answer, but it's actually very difficult. The reason for this is that when we look at these optically under our confocal microscope, of course, we're limited by the diffraction limit. So one spot of light coming from one of these is about 200 nanometers wide when we look with our microscope. But we know it originates from something that scale is on the order of nanometers. So within this 100 nanometer spot of light, somewhere in there is our defect. And if we come along with a different technique that can look on that length scale, for example, transmission electron microscopy, TEM, then we come in and we fire electrons at this material and look at how they diffract and then build our image of our atoms. Well, this very technique actually changes the material. And so what we then observe is not what was emitting light in the first place. So it sounds crazy, but we actually at the moment are stuck with seeing the defects by eye. But that doesn't mean we can't figure out what they are. And another field that has done exactly this, and some of the people on the call might be familiar with, is diamond. So another defect material with defects that's been very useful for quantum optics is diamond, because that also has defects. And it's now known that the defects are due to a nitrogen atom sitting in the carbon lattice. And the way that was determined is kind of backwards. So they realized that if they do a lot of nitrogen bombardment, ion bombardment of diamond, then they would see these color centers formed. So it's a kind of the opposite way of, like, from top down rather than bottom up. So we are currently working on some of these approaches. At the moment, we think carbon might be important, might be a carbon atom involved in our defects. And so it's a very good question. And the leading contenders are, it's a carbon next to a vacancy. But there's a lot of work going on to figure out what that is, including computational work, density functional theory, to run calculations of what type of structure would produce the emission spectra that we see, for example. The second question, I think from Mike Edwards, about, is this a spin half defect? Another excellent question, and that's exactly what we're trying to figure out right now. So that obviously Mike Edwards knows a bit about these things, because that's a very on-point question. And we are using our optically detected magnetic resonance signatures to figure out what the spin is of these. And at the moment, it is looking like it's either a spin 1/2 or it's a spin 1 with a very small zero field splitting.
And I think that also answers Pavel Kruper's question, which is also about, is there some understanding of how a defect can have spin? And that sort of covered as well. Yeah. Excellent. Let's have a look about what else have we got in here? So many good questions coming in. I'm trying to decide which ones to go to. Is there any that you particularly want to pick up on there?
Oh, sorry, that's cool. Let's turn that off. So someone's asked about, can you use graphene and HBN in multi-layer form? And if so, do you need to insulate the layers? So that's a good question. And absolutely. So graphene and HBN are very often used together. And actually before the optical properties became interesting, its most common use was as a layer in a graphene heterostructure, used exactly as an insulator to insulate graphene from other materials that you might want to use in your heterostructure. So when I talk about heterostructures, what I mean is like a sandwich. If you imagine a sandwich of 2D layers. You've got your bread and your lettuce and your tomatoes and your cheese, and each one of these is a 2D material. And because graphene is such a good electrical conductor, often graphene would form the electrodes of a device. And then inside that, there'd be a layer of HBN, because you want a clean layer between graphene and what comes in the middle. And then in the middle, we would use another 2D material, which I haven't introduced today, but there are other 2D materials that interact with visible light, can emit single photons, and a good electrical conductor, so they can be used to form, for example, atomic scale LEDs. And so, yeah, this has also been worked on in Mete's group. And so absolutely, graphene and HBN would be formed next to each other, and you don't need an insulating layer because HBN effectively is one. Right. So, yeah.
And Mike Bailey says, how big can you make HBN? And obviously you've indicated some of the flexibility of it there.
Yeah, well, that's another very good question. So you can make HBN a few different ways. You can either start with a crystal, and actually this is feeding back to how graphene was first isolated. They had a kind of a bulk of graphite, and they managed to cleave single layers off using sellotape. It's kind of the famous story, and that is indeed how it's done, and it's still done like that. And you can do the same with HBN. You can start with a crystal and then cleave layers off. We favor at the moment a different form of fabrication called chemical vapor deposition. So you have a surface prepared in a chamber, and you put in your precursor molecules that contain the atoms that you want, and then they get heated up and they eventually condense onto the surface in a highly controlled environment to form this 2D material. And graphene can be made like that, and HBN can be made like that. And so there, in that way, the size is actually endless, because it just depends on how large you're growing on a wafer. And that's really the form of growth that can be used industrially. So it's the scalable way of growing these materials, which is important. That's probably been, for graphene, I would say that probably one of the reasons that it's been held back a bit in deployment industrially is that scalable methods of its growth have been slower to emerge.
And following on from that, JL Davies says, how does the 2D material how can it be used as batteries, and what would the limitations of those be?
Okay, yeah, so that's a good question. I know, so graphene it's not being thought of to be used as the active material in batteries, but more so in improving electrode materials and to help prevent degradation. One of the big problems in research on batteries at the moment is that they suffer degradation, and so the ways of mitigating that, and it's thought that graphene could be useful there. I'm not quite sure any more of those details, but that's I think how it's been thought of being used for batteries. Yeah.
Right. Okay, there's a couple of questions about just going back on the defects. Ian Ward Campbell says, is the process of analysing defects illustrating the idea that just observing phenomena at this level changes the object's state?
Is the process of analysing defects illustrating the idea that observing phenomena changes the object's state? So I guess the question there is, do defects help confirm this hypothesis of quantum mechanics?
He's actually put a follow-up in there to expand it. And with these quantum behaviors, could we be looking at the possibility of instantaneous communication over very long distances?
Okay. That second one's a good question. So the answer to the first is no, I think. So so the idea that the observation of quantum phenomena and the measurement of a quantum object in a state thereby changes its state is not new. It's very much predates this type of research. And so the defects, the observation of defects themselves doesn't verify that hypothesis. It's rather that the fact that the way quantum cryptography works, i.e. via encoding information in a quantum state of a photon, the fact that that can work and that it does provide ultimate security is more of a confirmation, actually, of this kind of law of quantum mechanics, that measurement changes the state. And there was actually a good question to that from Lee, CMG Lee, asking why the eavesdropper simply can't absorb the photon, measure it, and then send on one that's identical onto to Bob, and thereby seamlessly pretending, that there was no eavesdropper. And that sounds like it could work, apart from the fact that the photons being emitted by Alice are inherently random. So the eavesdropper cannot reproduce what Alice is sending, which is the important point here. So the state of the photon being produced by Alice is not deterministic. It's probabilistic and it's random. And so it's impossible for an eavesdropper to generate the same quantum states from their end and send them on. I hope that helps with that question.
I think that sort of follows. So to hear Canan has a question: will the emission of photons have a pattern similar to how a binary is used in computers to communicate a message? And I'm guessing that's what you're saying there. There's an inherent randomness to it.
Yeah. So that question is getting more onto the difference between bits and qubits, which is in the realm of quantum computing, which I didn't really talk about today, but definitely related. So that's probably the best way to actually understand the difference between quantum computing and classical computing. Is the moment classical computers carry out logic operations with zeros or ones, and binary bits with a definite value. And in quantum computing, which uses qubits, logic operations are carried out with a quantum state that's a superposition of 0 and 1. And so qubits are that's the best way to think about it. So instead of binary 0 or 1, qubits have superposition of these, and so it has many more possibilities or many more states that it could take up. And then in a quantum computer, you take many of these qubits and they get interacted together to form a system that is mathematically very complex and very powerful.
Thank you. There's a question from Jared Jeretnam, who says, what causes light to become anti-bunched?
Yeah, so effectively, this comes down to the source being only able to emit one photon at a time. So if you consider an atom or a defect, like I've talked about, ground state, excited state. In order to emit a photon, the system first has to absorb energy, emit that photon, and it can't emit a photon it can't absorb another photon until that first one has decayed. So there's kind of this barrier. The system can only absorb while there's an electron in the ground state. When the electron's in the excited state, it's then not absorbing. It's saturated. So if you have a single quantum object, like a defect, like a molecule, like an atom, that is limited in how many kind of excitation cycles that it can perform, then that will be a single photon emitter. Now, if I took lots of defects and I put them all together, then I've got multiple quantum systems, and this is no longer an anti-bunched light emitter. Individually they are, but together they're not. And so that's an important distinction there, actually. So some light emitters that fall into one of the classical situations is there because I've got such a high density of single units, if that makes sense. So it's really being able to isolate something that is limited in how fast it can absorb some energy, emit that photon, reabsorb energy, emit that photon. So there's always going to be a space and time between each photon emission event, and that time spacing is actually the lifetime of that emitter.
And following that, Peter Tribe's got the question, do only anti-bunched photons show quantum entanglement?
Yes, yeah.
Okay, well, I'm going to keep Glenn Butterton's first question to be the last question. That's all right, we've still got a couple more minutes. So I'll just give you a second, Hannah, to have a look through there and see if there's anything that jumps out at you in the other questions. There's still loads coming in, so thank you very much, everyone. This is really good.
I think I'm looking at them all. There's one more about my path in science. We can answer that at the end if you want.
Yeah.
Could one defect emitter stimulate another? Yes, certainly. I mean, we haven't been able to observe that or know that that's happening. The major constraint to that happening would be proximity. So at the moment, these defects are well enough away from one another that the light emitted by one cannot be absorbed by another because it's simply too far away. But in practice, that could happen. In theory, that could happen.
And Camille's come in with a question following on from the anti-bunched light question. How consistent is the gap in anti-bunched light? Is there any measurable variation at all, and what determines that gap? Yeah,
so definitely. What determines that gap is the lifetime of the excited state of our defect, as I said before. So if we have a system that absorbs energy, electrons in the excited state, and then emits a photon, and then goes through another cycle, the limit here, the rate limiting step, is the time it takes for that photon to be emitted, which is called the radiative lifetime. And that is that can vary. In our system, we seem to find that most defects have a lifetime of a nanosecond. So small, short, and that doesn't vary too much, but that's something we measure routinely as well. Typically, if the lifetime is a good proxy of other things happening in the excited state. So if the lifetime is much longer, then it could mean that actually this electron has been promoted and then it's gone off to a charged state or done something unfavorable. So lifetime is an important proxy that the system is operating as it should.
Great. I'm going to do 3 more questions. I'm going to do, first of all, Christopher John Green, who said, you mentioned poverty as a possible application field. Could you elaborate? Is there something in there?
Right. Yeah. So I guess one area that is important is providing energy to third world countries. And one thing that I worked on a bit in my PhD was materials that can be used for solar energy harvesting that are flexible and that are portable and that are cheap. And so it's thought that if 2D materials can be engineered to act as light harvesters, not just light emitters, then they could be a very good way of getting solar cells distributed around the world. One of the major constraints with silicon, although now it's a lot cheaper than it used to be, it's not very flexible, it's reasonably heavy. It's not like you can make it into a paint and paint it on a roof, but other materials that are developing potentially have that kind of those properties, making them potentially easier to get out of first world countries and into the developing world.
Well, I mean, that's a real positive to sort of hear, and you hope that's where things go and people get given the time to actually come up with the solutions to this and to work through what's being done. Rather than another new technology taking over before you can get a chance to finish it, which is often must happen through this kind of research.
Yeah.
I said there was going to be 3 more questions. I've just seen that 2 people have sent in a very similar question on the basis of your previous answer about are photons emitted in the same direction, and does the light emitted emerge at a particular angle perpendicular to plane or across a range? That's Mark Foster and Nick Acast. Thank you for those. So I don't know if you want to just quickly touch on those before I go to the final 2.
Yeah, so that is a very good question, and so what we do have to do in the lab and make sure we do is have very good collection optics. The mark is correct that when you have a light source and it's emitting light, this light is actually going in all directions. And for example, we can't do our experiment exciting HBN and have our detector space far away from it and expect that the photons will reach that detector. So in the lab, we have on our optical table a series of very carefully placed lenses that sit very close to the sample, that collect the light that is being emitted in all directions, and then focus it down our optical fiber. So definitely at the point source, the light is in all directions, and then that light is collected and typically put into an optical fiber where it is totally internally reflected and well controlled before it reaches the detector. So yeah, collection optics are very important.
Excellent. Okay, so this one, there's a question from Isinger, which says, is this type of technology being used in computers, etc. yet? And also Glenn Butterton has said, if we could speak candidly to workers at GCHQ or the NSA, would we find they are already using quantum cryptography? And those are questions that you may not be able to answer, but the other one.
Well, quantum cryptography is definitely being used. So probably the leaders in that have been Switzerland and China, I think. So they definitely are already using quantum cryptography, but with what I would call non-ideal sources of single photons. So the typical, what's used at the moment are lasers, and I said they were classical, but they're highly attenuated. So many filters so that effectively you cut down how many photons are actually being sent out from this laser because you're putting lots of filters in front of it. So eventually you get one at a time. So it's not a true quantum light source, but it's a kind of a make-do situation. And that's what is currently being used. There are other technologies being investigated, but that's exactly why I think we need a better source, one that is a true quantum light emitter. So yeah, quantum cryptography is being used. This technology is definitely not being used in computers. Quantum computing at the moment, the state-of-the-art quantum computing technologies are not using photons. They're using superconducting qubits or trapped ions for multiple reasons. They're better for those technologies at the moment.
Great, thank you very much. And the final question is, I think you've alluded to it already as well, is also from Glenn Buston. Thanks for this, Glenn. It's a really nice question, actually. Can you tell us how you got interested in science as a child and what your path was to university and a Trinity Fellowship? And Glenn, I'm going to steal that question. I'm going to ask that every single time we do one because I really like that.
Yeah, so that's a nice question. I started getting interested in science. I was in New Zealand. I did my schooling there, and I went to university and did a Bachelor of Science in chemistry, actually. So my origins are chemistry. And I found the course there very interesting, and I guess I liked the way, especially the kind of physical side of chemistry, where you could think of principles and concepts and then see that actually taking place in the laboratory. And I liked kind of optical chemistry and optical physics because often your observations were very clear cut. Unlike in other areas where, you know, the reality is kind of a mixed behavior of a lot of systems, with this we could actually, you know, see very clearly a resonance at that energy or resonance in that. And so I think that caught me during my undergrad. In my undergrad, I was still interested in other subjects as well. And so it took me some time to decide on chemistry, but I eventually went in that direction. And then saw my PhD supervisor giving a talk in New Zealand, so Richard Friend, who's the Cavendish professor. And he was talking about using materials that I had been studying for OLEDs and for solar cells. And it really appealed to me that the somewhat abstract science we were doing in the lab could actually translate to something very practical and useful, which I guess is kind of what this talk has been about. I still find that interesting. And so that was really the hook, actually. And then I applied to Cambridge, which was, I was incredibly lucky that my application was seen, and I came here for the PhD. And then that led on to the Trinity Fellowship, because after my PhD, I took a bit of a change in subject, but I still wanted to explore light emission and how, you know, different types of material systems, and that's how I got to 2D materials.
Excellent. And you haven't looked back since. You've been at Trinity now since 2017, as I said earlier on. So thank you very much for doing this today. I think we've answered all the questions. There's been so many coming in, which is really great to see. Thank you everyone for sticking around. We've got great numbers still on the call as well. So if we were in the Winstanley and doing this in person, there would be a nice round of applause now, but you know, one day I'll bring a virtual applause app to one of these and we'll hear some sound at this point. I'll maybe ask someone to edit it in at the end. So thank you very much, Hannah, for your time with this. Thank you everyone for attending. And thank you also to my team back in Cambridge for putting this together, Matt and Rachel. We've got no more of these planned before Christmas, but I'm hoping that my colleague will now put up there we go, perfect, there's the screen. We've got 4 more lined up, which is really good for the new year. So there's the dates for your diary. They will all appear on the Trinity website soon, if not already. And I look forward to hopefully seeing you at one of those in future. Thanks again for joining us. Have a great Christmas and New Year if you're celebrating that when it comes around, and we'll see you in the new year. Thank you very much.